In this section, I'm going to show you how to find the pump operating point, which will then allow you to determine the volumetric flow rate for the pump for a particular pipe network. So to do this, I'm going to consider a generic example and then show you how to solve it in a generic way so that you can apply it to the particular problem you have. So this is a sort of typical problem that you'll have. So you've got water in tank A that you want to pump up into tank B, so through our pipe network in between, and the level of water in tank B is a given height above the level of water in tank A, and tank A may or may not be under pressure. So in this example it's closed, so you've got some pressure in here, and obviously if this was open to atmosphere then P1 would be equal to P atmos. And we also have some pressure in tank B or the second tank, and that again could be atmospheric pressure, in which case P2 would be also equal to atmosphere. So I'm going to show you in a generic way to find what is the operating point of the pump, and also what's the volumetric flow rate of the fluid between the two tanks. So the pump has to overcome, if you think about it, what it has to overcome is the hydrostatic pressure. So in other words, it's got to raise the fluid by height h, increasing its potential. It's also got to overcome the pressure difference between the pressure in the two tanks, if there is a pressure difference, and also needs to overcome the losses due to the pipe network, and that is, if you remember, that's a combination of friction and also the minor losses of any bends, filters, valves, etc. in between. So we solve this using Bernoulli. So most of this you'll recognise before. So first thing just to state is where we're taking point 1 and point 2 from. So point 1 will be on the surface of the liquid in tank A, and point 2 will be on the surface of the liquid in tank B. So in Bernoulli's, we've got our static pressure plus our dynamic pressure plus our potential is equal to the same at point 2. And we've seen previously they've been introduced in this pressure loss term, which is due to the friction and minor losses in the pipe network. But you see on the left hand side we've now got this new term, and this is the change in pressure due to the pump, or the pressure rise due to the pump. So I'm going to show you how to, as I say, solve this in a generic way. So this is the equation we had on the previous slide. And going from tank to tank, one of the assumptions that we can make, if you recall, is that the area in the tank is very large compared to the area in the pipe. Therefore, the velocity in the pipe is very large compared to the velocity in the tank. And in fact, we can assume that to be negligible. So the velocity in tank A, or C1, is 0, and also C2 is equal to 0. So therefore these two terms will disappear. So that's it written out here with those terms gone. Now what we're trying to find is the pressure rise that's needed to move the water from tank A to tank B. So we need to make this pressure rise the subject of the equation. So rearranging will give this. So it's the change in pressure between the two tanks plus the change in height plus the pressure losses. Remembering that Z2 minus A1 is H, so we fill that in. So this is what it's going to overcome, as we said, the static pressure between the two tanks, the potential increase, and also the pressure losses. Okay, so from the previous slide, this is what we had. Now, if we recall that we know what the pressure losses are, this is a generic equation. To look back at the other lecture if you're not sure where this has come from. So the generic formula for the pressure losses is that it's the frictional losses, so the friction factor times length over the diameter, plus the sum of all the minor losses times by the density times by the velocity in the pipe divided by squared divided by 2. And you need to do this for each section of pipe. Remember where a section is of a common diameter or a common material. Now we're interested in the flow rate, so we can also we're substituting c squared is equal to v squared over volumetric flow rate squared over the area squared to give us this. and then we substitute this into our Bernoulli's equation here. Okay, so this is what now I have it in terms of volumetric flow rates. So this is what we had on the previous slide. Now what we're going to do here is we're going to combine some terms. So in this square bracket we have terms which are not dependent on the volumetric flow rate. So it's just dependent on the pressure between the two tanks and also the height of the water levels between the two tanks. And on this side we have, in this bracket, everything that's this term combined is obviously a function of volumetric flow rate. So if we take these out as constants, then we can write it as this equation. So the pressure rise for the pump is equal to K1, which is not dependent on volumetric flow rate, plus a constant K2, which is dependent on volumetric flow rate squared. And this equation here we can sort of describe as the pipe characteristics for our given pipe network. So now if we plot that, so this is the red line, this is the pipe characteristic curve, so it's some constant plus another constant times the velocity squared, so that's the red curve. And if you recall early in the lecture I gave you a generic formula for the pump characteristic curve and showed you that that's the green line shown, so it's some constant minus another constant times the velocity squared. So we have effectively our pipe characteristic curves and our pump characteristic curves. Now the operating point for the pump is the position, is the conditions where these two curves cross, or in other words where they're equal to each other, so the pressure rise. So if we set these two equations equal to each other, this is what we get here, or shown graphically you can see it's the point where the two curves intersect. So for our particular example here we would need this pressure rise, whatever it is, to overcome the potential, the pressure difference and the losses in the system, and the resulting flow rate would be this if we were to read it down onto the x-axis. So you can either solve these types of problems two ways, either mathematically, so obviously you've got an equation here, so you'd know A1, A2, and you'd be able to work out K1 and K2 from the values from the question, so you can just solve for V squared. Or if you prefer, you can plot it, so you could plot, again, if you know what K1 and K2, you can plot that on a graph, and you can plot, you'd know the pump characteristic curves, you can plot that, and then you can find where the two intersect to get the volumetric flow rate. So this will, as I say, is the pump operating pressure, and this is the operating volumetric flow rate. However, you might want to also know what the efficiency of your pump is at the operating point. So if you have the efficiency curve for your pump, then you can read off, so you would first read off find where the two intersect, read off the volumetric flow rate, then on your corresponding efficiency curve, you'd read off for that given flow rate what the efficiency of the pump is for that particular speed. Okay, so that concludes this lecture. Thanks very much for listening.